In this video, we'll have a look at intakes and some of the problems with regard to these. As was mentioned in the previous videos, although there are many practical problems to overcome with intakes, these are generally considered to be soluble. And so we won't spend so much time talking about the intakes as we will talk about the mixing section. Also, as I mentioned in the previous video, there is an excellent treatment of intakes in the University of Queensland videos, and these are referenced in the previous video. So first, let's consider the purpose of the intake in a bit more detail than we have so far. Firstly, it's there to compress the flow and ensure that the correct pressure and temperature are present at the combustor. Secondly, it's there to control the intake velocity so that it arrives at the combustor at the correct speed. Thirdly, it has a purpose to turn the flow into the engine and to ensure that the flow is uniform and parallel internally in the combustor duct. And finally, there are a number of other problems which it seeks to minimize. One of those is to avoid unstart, in other words, the duct stalling, and to be able to have a uniform start for combustion. It also needs to have minimum drag, and there are many causes of drag: skin drag, wave drag, form drag. And these are all critical to engine performance. Skin drag is particularly important to control, and it is essential to make the engine as a whole as short as possible to minimize this. Finally, it must perform compression efficiently in other ways. Remember that it's part of a Brayton cycle, and so it needs to perform its function as isentropically as possible, so that all the energy is retained within the fluid flowing through the duct and not lost in heat or internal friction. So let's look at the general types of inlet, and indeed these apply to the whole engine. This is not an exhaustive list, but it just outlines some of the basic types, which I'll draw on the diagrams. First, there are planar types, which are flat and linear and typically built in to the airframe of the craft. Then there are symmetrical planar types, which are a subsection of this. And finally, axisymmetrical types, as shown in the diagram. These are less popular at the moment as designs than the planar types. All these inlets work using the same principles, that of shockwave compression, as we discussed in one of our previous videos. I'll go into slightly more detail now as to how the shockwave mechanism works. As the flow passes through the shock, it turns and the temperature, pressure and density increase. In other words, it gets compressed, although the velocity decreases. The relationships are given by a standard set of equations and a diagram called the m theta beta diagram. This diagram shows a relationship between the Mach number m and the two angles, the angle of a shock wave and the angle at which the surface is turning, as shown in the figure. Once we know these angles, we can put them into the appropriate equations along with the Mach numbers to give us all the ratios that we want to work out, like pressure and density and temperature. You can revise the principles of these in Anderson's books or in the University of Queensland videos. You can find the references to all these in the previous video. Let's now have a look at the topology of some typical intakes. The first one is a discrete external shockwave system. In this scheme, a series of separate shocks is set up by steps in the intake compression surface. As the air passes through each of these, it gets compressed and it turns. The compression surface is designed so that the shockwaves terminate at the outer lip of the intake cowl without hopefully reflecting. As we will see later, the more shocks which are used, the more efficient is the intake. This system, however, results in long external compression surfaces. Another type is the isentropic compression system, which I mentioned in a previous video, and this is simply the conclusion of adding more and more steps to the system mentioned above. And as we do this, the duct becomes more and more efficient until finally the duct ends up as a curved surface and the compression is isentropic and therefore very efficient. The design of the correct curve is quite involved, and I'll give a reference in the description of the video below if you're interested in pursuing that. Next one to look at is a combined internal-external compression shockwave system. Allowing reflected internal shockwaves can increase the compression efficiency and allow for smaller flow turning angles. This results in longer intake lengths, however. And finally, we have an internal shockwave system. This can produce short intakes, but is difficult to model due to the potentially complex nature of the internal reflected shockwaves. One thing should be obvious, however, with a little thought, and that is that it's impossible for any of these intake types to operate efficiently from sea level to the edge of space without an extensive variable geometry type of reshaping of the duct. Now let's have a look at some of the major issues which affect the ducts. The first problem is that because of the high speed involved and therefore the high Reynolds numbers, the boundary layer becomes very large at high Mach numbers. In fact, it can become so large that it alters the whole shape of the duct. The stationary nature of the edge of the boundary layer also means that there are potentially high temperatures at the walls of the intake. And this changes the flow parameters and can cause chemical reactions. And these in turn can result in increased flow viscosity and flow complexity. The temperature rise and the turning angle of the flow must be carefully controlled, or we will get boundary layer separation, and this can cause the engine to stall or unstart. It can be shown mathematically that the compression efficiency has an extremely important influence on the whole engine efficiency. So much of an influence, in fact, that it can determine whether the engine is tenable at all. And further, you can show that the compressor pressure ratio and the compression efficiency are related by an equation. We can plot this out in a diagram. And from this, you can see that small inefficiencies in the compression side will cause large losses in pressure in the combustor. And it's obviously essential, therefore, to keep this as high as possible. Further development of equations show that good compression efficiency requires at least 2 shock waves in the intake compression surface, and preferably more, and in fact preferably an isentropic compression system. In order to protect the intake from back pressure further down the engine, which may cause unstart, as I mentioned previously, a protective section of straight duct is often included between the intake section and the mixing section. In this section, a series of shockwaves is set up which serve to decouple these components from each other.